Okay, I wanted to redo the, the lecture from this morning because it just felt unorganized and disjointed. So I want to go through equivalent systems of force, and then we'll talk about couples or pairs of equal and opposite forces, and review what a dot product is. And I made another video for this really hairy one of finding the moment, not around the XYZ axis, but around some other direction that requires using dot and cross products, which is kind of confusing. Okay, so equivalent systems of force. What we have here, and this is going to translate in the future into center of mass problems. So where this is going and why we care is, so far we've been using what's called a concentrated load. So that is where the entire force acts at just a single point. In the future, we will look at problems where we have like a pile of sand, where each piece of sand in this pile has a weight and it has a force. And this is a very complicated system, right? You don't want to have to keep track of every single brick or every pile of sand. So you want to simplify this to have just one force acting on the system, where this one force, maybe this is the force of one piece of sand and another piece of sand. Okay, so this is going to be the combined load of everything together. So we're adding up the forces from each little piece of this thing all together. And we don't just want the magnitude of the force, we also want the location of it. So if you've done something with center of mass before in physics, that is where this is going. So rather than 100 different forces and each one is maybe creating a different moment, we want just one force, and then the location of that force will give the exact same moment around the end as all of these little pieces added together. So equivalent systems. And we'll start with, instead of, thousands of pieces of sand, we'll start with just 3 forces, and we want to take those 3 forces and turn them into just one force, and we want to figure out what distance that one force will act in. So the magnitude of this thing is going to be all of these guys added together. So let's say this is negative 100. Sorry if that text is small. And this is negative, it's going down. And then this is positive 100, it's going up. So if I add all those together, so I have 100 going up, minus 100 going down, minus 100 going down. So we end up with negative 100. So that's just the summation of all the forces in the entire system. We're getting an equivalent force. And now we want to get an equivalent moment too. Okay, so if I go and I say, okay, we've got a distance of 2 to this first force, so 2 in the I direction to negative 100. So this is going to give us a moment of negative 200, right? And then I can go, maybe I'll use a different color here. I'll go to the next force over. So this is a distance of 4 to 100 coming up. So this is actually going to be a moment in the positive direction. This is a positive 400. And then I have another one. If I come out here, so now I have a distance of 6 to 100 going down. And that's going to, again, give me a negative moment. So here's our negative 600. And if I add these all together, so a moment is a vector. If you have everything is in the k direction, k plus k plus k, this is the overall moment from all 3 of these guys added together. So then I ask myself, okay, so what distance does this equivalent force have to be at if I am going to have the exact same moment happening here? So I want a clockwise or negative moment of 400. We'll call this Newton meters, force times a distance. And that means that I have to put my 100-pound force at a distance of 4 away. So the point of all of these are they are not equal to each other, they're equivalent. They will, if I was to figure out what the force at the supports is here, I would have the exact same reaction in this system as I would have if I solved for the reaction of the supports over here. So it feels the same. If you were a person and you were like over here holding this up, it would feel exactly the same if you were holding up the side of this concentrated load as it would feel with all of these things. You wouldn't be able to tell the difference if you were just hanging on to the end of this thing. Okay, so hopefully that is clear for equivalent forces. So you're taking a bunch of chaos and changing it to one force, and that force is a magnitude of everything added together, and the distance that that force acts on, that will give you the same moment. So it's the same moment, and you can take the moment around end B or end A. It doesn't matter which side you take it around, it'll be the same moment one way or the other.